Thank you for the invitation of the talk. Pleased to talk about our paper. I've been trading crypto and futures market for many years. Recently, we have been looking into new opportunity in AI and machine learning domain through publication and patent. I cannot monetize from it yet. I'm looking for some. We have been tested a new machine learning algorithm. We have developed it and we apply for a US patent. These are the outline of the talk. I'll review the basics and I go to our paper very briefly. And after hearing this talk, I'm pretty sure that you get some core idea of how ChatGPT works fundamentally. So it'll be easy. The human languages have few 100,000 to a billion vocabulary words in the dictionary. So prior to 2013, language modeling was limited to manual word numbering as this way from A to the last one, or the unit factor representation in really large dimensions. Say if the number of vocabulary words in the dictionary was 1 billion, then it should have been embedded in 1 million dimensional unit vector. So this is so computer science guys call it one-hot encoding. So that's their jargon. The problem is that it doesn't represent any meaning. This representation is nothing but random ordering of vocabulary words.
I have a question. So for one hot encoding, what you are referring to, so in computer we have for each alphabet ASCII codes. So why not use ASCII codes rather than one hot encoding?
You may use the ASCII code for each alphabet.
Yeah. So
alphabetical.
Let's say Aaron. So A has one unique ASCII code. R has unique ASCII code, so I will require 5 ASCII codes.
Okay, so why all of those representations are just random? Is all the same as labeling a random delineation of each numbers. ASCII code doesn't mean anything.
Okay.
So yeah, that's. So this machine learning concept has started in early 19th century, and even neural networks has started in 1940s, they say. And lots of progress has been made since then in speech recognitions and image processing, but language modeling stagnated until 2013. So all of you may remember the AlphaGo model, so Hadoop. And that was an image processing neural network. It is not a language model. So AlphaGo model was very successful, but it didn't have a language model. It means that before 2013, there was no way to represent vocabulary meaning in any way digitally. And back then, this was a great frustration to many people who want to investigate or monetize in neural networks. So yeah, so and that was the huge issues back then. And proposition.
왼쪽에 최소화 버튼. 왼쪽.
Without this invention, ChatGPT wouldn't have been possible. So yeah, to understand how this we qualify. So to understand how this idea works, let's just imagine a very small book with very small number of dictionary. So we suppose that we have these 17 words, and we suppose that we write a book only using these words. And the book can be as large as possible. Let's say we should finish up to 15 sentences this way, and just take a look at these phrases. It'll appear later. Then this unit vector representations in 17 dimension will be like this. So and the delineation and the sequence doesn't matter. And So to construct a semantic space, we consider a linear transformation from 17-dimension unit vectors to smaller d dimension. So we choose that dimension to be 3 as an example. And then that linear map can be written in this matrix, right? And the thing is, we are initializing the entry of these matrices with random number. Then these are the figure represented in 3 dimensions. So we may draw embeddings in this figure. And what you want to do is to design a probability model on these configurations. That's the goal. And just take a look again at these 2 arrows that represent word row and state. So what we want to do is to migrate the context in the book into the context vector. So which means we can define a context vector in a very simple way, just taking arithmetic mean. So we can take these context, row and state, which appeared several times in the book, as is shown right there. That context is, except the middle words, can be written as another vector and as an arithmetic mean. And the thing is that we have to compare this context vector and the really appearing row embedding vector.
Sorry, it's a little bit difficult to follow. So you label the words, various words in vectors. I do understand that. Then what is the goal? So this is label for various words. Now,
and the goal is to construct a probability model.
what do you mean by probability model? Yeah, that.
So the probability, so proper probability model that fits into the contents of the book. So yeah,
the transformation from 17 to 3, you mean that you pick 3 words out of the 17 and you see.
No.
What is exactly this transformation? What is the meaning of this transformation?
So at first,
So you start with 17.
okay.
So why do you have number 3?
Number 3 is arbitrarily chosen dimensions.
Okay,
So-
but once you choose it, what do you do with that? So you choose 3, okay, and then what is the
So this is the unit vector representation of each word. So in the same way, we can define. Oh shit. So we can define the same unit vector representation for the 17 words that way, and these unit vectors do not carry any meaningful geometry, right? So we are going to put these unit vectors into some small side space where the semantic meaning appears. That's the goal. We do not know how it is done yet. Yeah, it may embed it in just 2 dimensions or 1 dimension, even 1 dimension, but it should be much less than 17 dimension. That is the goal. So
you start from 17 unit vectors and you end up with 17 vectors with the
Yes.
arbitrary orientation.
Yeah,
I'm
arbitrary.
very interested to see if some vectors have a line or something.
Yeah. But the dimensionality is not fixed. So dimensionality. So in practice, they find the dimensionality trial and error. So yeah, there's no guiding principle to choose the subdimension D. So we just choose it to be 3.
This is done for improving the training actually, the dimensional reduction. The feature space has been reduced to a smaller dimension, from
Yes.
17 dimension to a smaller dimension,
Yes.
to increase the training speed, I think. Training and the,
No.
then I think CNN also will do that.
So this 17 dimension does not have any semantic informations. So we want to squeeze it to the smaller
Smaller
dimensions where the semantic meaning appears. That's the goal. So it's not about
distance between vectors. It will be given by
Something like
distance.
this.
yes.
And here the distance is all uniform, yeah?
Yes.
Yeah.
That is correct. That is
Put them
correct.
apart.
Yeah, yes. So the point is to find a way to align those vectors that could represent the meaning in the book. That is the goal. So okay, sure. So the idea is to compare the context vector and the really appearing middle word representation vector. That is the idea. So and so suppose that we have some probabilities that is assigned to every single words in the dictionary. Conditioned on context vector. So yeah, let me just go back again to the book. The context may contain row and state in these sentences, and some sentences will not have that phrase. And in some phrase, it'll have no words in it, or it may have some energy in the middle, right? And we may count all those different occurrences for each different words. So it is possible. Okay, in principle, it is possible that in the middle, low state may occur, but in real world, it'll never occur, right? So in that way, once you have a context, then there should be a probability that some words will be higher than others, right? So that is the probability that I'm talking about here. So in this way, so this conditional probabilities may be defined numerically. So let's not just care too much about the functional formulations of these probabilities, but let's just assume that these conditional probabilities have some numerical values. So you may have a p-good distribution for each word, right? Or it may have p-bad distribution this way.
Now, I understand what now P means, but what is the difference between P good and P bad?
It is just an example of we do not know the exact formulation of this conditional probability, but however it is a probability, so it should sum up to 1. and it should be distributed to every single words in the dictionary.
Yeah.
Yeah, so, yeah, so we may assign some numerical values for each word that sum up to
We
one.
cannot randomly assign numbers to each word, right? Like, for example, for given two options, like two words like low and state,
Mhm.
as you said, energy could show appears very frequently,
Mhm.
but some other words may not appear at all, right?
Mhm.
So for each word in our out of 17 options,
Mhm.
there must be some words who appear very frequently, some does not.
Yeah.
So we cannot just randomly assign probability to
Yeah. That's right.
exactly. So P good, that one. I mean,
Yeah, this one is better. I mean, if so, these are the real observations. So let's not just think too much about the real dynamics of how this P good or P bad is made of. It's just a choice of different probability models.
actual count is actually that.
Yeah. Sure.
But by the way, so does this context vector include information about the word order?
Mhm.
So you have like low blank state,
Mhm.
but you could also imagine some situation where it's like state blank. Does
Yeah, so this is not. This is just one example of constructing context vector. So as you said, you may consider the ordering of words, or even you can look at much wider context.
I see. So if you had like state blank low, would that be a different context vector?
Yeah.
Oh, okay, I see.
So it may look silly, but yeah. So we can just choose these different distributions, and these different distributions. Okay, so obviously, yeah, this model looks better than this one. So what we care is the so-called likelihood, and likelihood is the probability based on this observation with predetermined model probability distribution that these observation is observed. The probability that these observation is observed given these number of predetermined probability models. So does that make sense? So it should go like this. So in total, it should be this quantity. And it is called likelihood. And this model and model data consistency is written in this way. And we should recall that the capital W matrix was initially a random matrices, right? So suppose we have chosen, fortunately chosen a random matrix whose row that represent V energy and V blank, which was the first row and the second row was close to V context. Then the model is a good model. Or otherwise, we chose a bad random matrices for omega capital W with this raw energy, raw vector, and this free blank vector are away from context vector. It's a bad representation. So in a well-trained embedding matrix, we want that we want this context vector and mostly observed word vector should align. That is the preferred model.
Here's a quick question. What is the best value of likelihood that describes perfect model? Like it says to measure a model data consistency. So that means
That means
value
the mostly observed word should appear the most. I mean, so
is
it,
it most
yeah, so
proportional or
yeah, proportion. So ideally, it should be 0.7, 0.3, and all the rest 0.
Oh, and
Yeah. That is the best one.
Yeah,
That should
I
be the best
understand.
one.
Then in that case, what is the value of math L? Because so in the next slide,
The likelihood.
the likelihood. So it's not going to be 1, right?
No.
So can I just say I just looked at likelihood? It's a single number, and it seems like I cannot tell based on the value of likelihood. I cannot judge the goodness of our model, right? I mean, how good it is. Can I do that? I just want to understand why it is a measure of model data consistency.
So
Like for example, if
yeah,
it's
so
very, it's if it's for good model, it's close to 1. Bad model, it's close to 0. Then I say, yeah, that's a good measure. But otherwise, how can I tell that's a measure?
It's just comparatively. So P bad is comparatively smaller than P good likelihood. If I define this probability, since these two numbers differ greatly.
I see, roughly speaking.
Yes,
At least for those two examples.
Yeah.
I mean, normally in such a computation of the probability, you multiply number of degenerates in front of this each individual probably to the certain power number of events. Then there is some degeneracy. But the degeneracy here is somehow all set to be 1. So it looks like you don't distinguish ordering. And
Yeah. So it's all comparative. So we want to. So if you have chosen this to be, so maximizing this quantity is the guiding principle. So we want that this dot product be higher. So it's natural to define the negative value of this dot product.
You see that this has to be maximized, right? Likelihood has to be maximized. I mean, while training something, you have to maximize.
Okay, so it should
Training
come.
of the model.
Oh yeah. I mean, okay. I have not specified any concrete functional form of this conditional probability yet. So the idea is that I'm going to get into the Boltzmann distribution because of these properties. So if we define energy as a negative value of inner product with a context vector and the word vector, and if we want that that quantity as a probability and probability function gets higher, then we may assume that there are some average alignment between these functions. Then it is natural to think of Boltzmann distribution. So
the minus sign is because if you have a line, the energy is minimized.
Yeah.
just because of that.
Yeah. So this is the final functional form we can infer from all the situations we have seen so far. So with this, with this functional form, we can now maximize the likelihood function. So all we do is the very typical things we persist to so there are so looking at these log functions, there are pressure that highest inner product should coincide with the mostly observed words, and it cannot go infinitely go higher, so because it will be suppressed by the normalization factor. So it can be looked at with if we see the gradient descent method. In fact, it is gradient descent because we want to maximize this quantity. And if we expand it and see it, then these row vectors should transform this way with this gradient ascent.
It should minimize the log likelihood. So it's log of the likelihood.
Yeah, log of likelihood.
Then if likelihood has to be maximized, then the log likelihood has to be minimized, right?
It's usually it's gradient descent it has a minus sign. The gradient descent convention goes minus sign usually. And or you can just literally just look at the meaning of this formula. So let's just forget all of that descent or ascent. Then we may look at it. You can just take a derivative and take eta as positive. Then the formula will look like this. And VL prime transform for the positive value of this VL prime increase, right? It means when VL prime increase, then the cosine angle decrease, so it aligns. If this quantity is positive, it means it should the vector should align to the context vector. So that's exactly what we want. For the opposite case, it should be repelled. So right? So the observation in the book phrase and the model discrepancy lectures on
Gradient ascent, not gradient descent method.
yeah, gradient ascent.
I'm still confused on how you define. So in this model here, the complex vector is fixed. And you change
Context vector. No, context vector is not. Context vector. Yes, context vector is fixed. Yes.
So how do you define it? So
Context-
can you remind me, because
yes. Context vector is randomly chosen. So if you are randomly chosen, so you should test these with various really many different context vectors.
oh, so I see.
Yeah. It's
You
like a
try
ton
all
of,
possible combinations.
yeah, yes. It's a ton of calculations. It's just one example.
So it's a fitting parameter.
Yeah, we may choose different contexts and do the same thing.
What is the goal? Is the context vector the goal?
So
Or
we are going to test all different context vector and doing this maximization for all different vocabularies. The final result is to find good configurations. So, and this configuration starts from a random distribution.
where is the context?
This configuration comes from a random distribution. So capital W matrix started as a random number. So among those random number, there happen to be a good alignment, which maximize all different likelihood go maximum. So
So here there are two issues. One is the mapping. You started with, so these vectors are random. The
Yes.
second is the context vector,
yes.
which is also varied. So there are
Yes,
so many things
but at
that
first,
happen.
but at first we need to fix the context vector,
Okay,
and then we can align all different vocabularies in terms of that context vector, and we choose another context vector and align again.
in other words, what you want to know is you take 17 words,
Mm.
you check a big book,
Mm.
and you want to understand what you're talking about. What these 17 words,
Mm.
and
Ah,
a space, a subspace of topics
Yes.
to which these 17 words belong.
Mhm, mhm.
Is this the point?
Yeah, that's the point. So, and if you see the result configuration, you will realize, you will see what it means. Yes. So after all this hard work is done, then this is the result table. So this is a quite famous example, which is frequently told in AI lectures. So, and we do not give these access by hand. The meaning just emerges. So I labeled this access with these words: gender, royalty, age. But this micro prescription does not specify any of these words. It just appears very naturally. So if you see these words, the similar words aligns in close proximity, as you see. The female words aligns to the left, and the male words align to the right. Okay. And because of this alignment, the famous vector arithmetic in semantic space is possible. So the king minus pen plus woman means queen. So it's and that really happens, and this happens naturally from this algorithm. It's not given by hand.
I recall all.
So
Explain more.
Yes.
Easily.
I guess it's like responsibility.
It depends on which book it's done.
So
So-
that, okay.
I thought somehow, so each word now its representative vector is now fixed, and this three vector components are all fixed here. I thought in the previous case you are fixing concurrent vector, which is somehow a parameter fits with the real data with this distribution. But how you would fix each individual vector? I thought you are fixing the one
Yeah,
vector.
Yeah, in other words, when you have a boy, is represented not only by gender, royalty, and age, but by many other things.
Oh, yeah, so it's just a heuristic representation. It's so,
We are just considering.
yeah.
But in this context, where is the context vector? Sorry, I'm still confused.
Yeah.
What is the context vector?
Yeah.
So here is a difference.
Context vector might have been any combination of these. So
And that's just.
so yeah, let's say we have chosen a context vector, father and a boy. And-
You are testing all possible pairing.
Yes.
All possible.
Yes, all possible pairing. Yeah, that's
Each
context.
pair defines
Sure.
context
Yeah,
vector.
that's
Each
that's
one
right.
of them
Yes.
is okay.
So, yeah.
Then I understand, but now, didn't you use this dot product of the two vectors to find a good model?
Mhm.
Dot
So-
product is
so-
a number, right?
Yeah, that product. So let's consider these cases. So let's say we have chosen father and boy as a context, then context vector might reside in somewhere in the middle. And then daughter so we do not specify, okay, we do not have a specific words in writing right there, but so this context vector should much differ from daughter, and it should be much closer than man or son.
Yeah, exactly.
That's
So closer, farther, that can be told. But now you have this specific meaning to each like axis, right? Age, birth, gender.
yeah. So that is an emergent property. So if we do lots of such things, then yeah, this continuous space emerges without specifying anything by hand. So that's somehow a magical thing. Yeah, that was not known until 2013. Yeah, people didn't have any method to do this before 2013. So that was a big problem for.
You specified small d equals 3, which is 3 dimension, and then you do this whole pairing and then fitting with the data, and then you determine these vectors for each word.
Yes.
And then on the naming, gender, royalty, age is done by
Exactly, that's
you.
the question I had. The problem is something more, like otherwise, for example, let's say you pick your context vector like man and boy. Then as you said, you have context vector in the middle, and there are different words. Some of them will closer to that point, some of them will farther.
Mhm.
But if you don't impose further like conditions, you cannot distribute these different words in different directions, right? I mean, like daughter is in that direction and king is in that direction. But how can you decide that? I have
All possible pairing.
all possible.
Because of the training, right?
Yes.
It's the effect of the training. It's the effect of the training, what he's asking. Unless we don't train.
Yeah. The point is that we have to.
So the point is you didn't specify age or royalty in the
Yeah.
first place.
Yeah,
You
no.
just did it,
Yeah.
and then you see that each axis has such kind of meaning.
Yes.
I see.
Yeah,
Okay.
that axis just appears.
So so suppose maybe it's better to ask this question. This is the final result of a successful procedure that found a good solution. Suppose that instead the procedure fails. How would that plot look like? Completely random. Right? So what is the goal? The goal is to have these points pointing into the direction of the three axes. So to have you have a cube there. Inside that cube is empty.
Yes.
This is the way that you say that this has converged. You have you have kind of classified these words and put them apart. If instead you don't find any pattern, these words are random, and so they are also in the middle of the queue. This is,
Yeah.
can I understand in that way?
And moreover, even though we do not have a word in the middle, but the meaning itself exists, even though we do not have the word.
But here the idea is that you classify these words by an emergent pattern.
Emerging by emerging.
I mean, this royalness, gender, or age emerges from the words that you're using. But if you use other words
Yes.
and you want to classify them with the 3 axes,
Yes.
and you finally tell them apart,
Of course.
you don't know what the patterns are.
So unexpected meaning may emerge. So that's a magical thing. So we do not. There is no way. I mean, we can identify all the axes with proper words. So this is just a heuristic examples. All we know is the relative distances and distributions of words. That is what, yeah.
Yeah, there's some questions from the audience on Zoom.
No, it's not. It's not from metadata. It's totally independent from metadata or independent labeling.
So your extra input.
No, there's no extra input.
I mean, this wording, gender, royalty, age, are they?
No, these are given to this column name is given to illustrate the results. All we have is just these numbers.
Okay. Which is extra input.
Yeah.
Humor.
In other words, they correspond to some concept.
Yes.
You don't know what a concept is, but
Yes.
if instead you try in all possible ways and you still have a random pattern, it means that that these words you cannot really put them in together in any way. So no meaning emerges. But then you can do that instead of 3 with 4, with 5, with 6, and whatever.
So it is known that nowadays they are using more than 50,000 meaning axes is used in this current age ChatGPT Gemini models. Means there are
Small d.
small d is 50,000, around 50,000. It may increase.
Since there's 10 minutes left, so just please go ahead.
Yeah. Oh, yeah, tell us. So far we have seen word embeddings in a continuous semantic space. So let's just consider a specific sentence. Since we have seen dictionary embedding, so let's just assume that a semantic space is just 2 dimensions. Then this sentence words, if we put a dictionary embedding, then it may look like this. Let's just assume. But the point is, this queen in dictionary meaning should differ from the dictionary, I mean, meaning should differ from dictionary meaning in this context. So this queen is speaking queen, and this queen is speaking to a young man queen. So the genderness or the royalty or age may differ. So this queen may be much older than dictionary queen, right? In that way, so if we represent this sentence in embedding space, it should initially start with this one, this way, but with this context, it has to change. So what this Google guys has done is to find a way how to do it. That's and this is the exact algorithm or the prescription that does this transformation. So this is the Homer representations. So the core concept of attention is this. If we pick this word, and this word should refer to all the rest context word.
When you define the attention, you have some like 2 or 3 additional vectors, a query vector. And can you go to that?
Yeah. So I'm not. Okay. So yeah, it's a computer jargon that people say there are 3 matrices: query, key, value. But I think that's a misleading terminology. I think. So yeah, it is just an extension of word embedding logic. So when the 3i represents the specific sentence word, for example, queen, and we want to compare the inner product with other context word, and that has to change. That should go under a linear transformation. So we can end up with very familiar and similar bilinear functional form for the energy as we have done in word embedding. And let's just push it a bit more, and then let's just construct with these bilinear constructions. And yeah, it may look like a Hamiltonian, but it is not scalar quantities. It is just a matrix. Yeah, let's 시간 다 됐죠. About 5 minutes. Yes. So yeah. So the Google guys, the innovation is so we may think of this form very naturally, and people have tested this model for some years. And what Google guy did was decompose A into 2-component matrices. That's the innovation. This one. So this one is called Q, and the right one is K. Yeah. So So yeah, usually this machine learning process is the reverse of the physical theory. We have lots of data input, and from that data input, we want to find this interaction matrix. The components of numerical. What we want to find is the numerical components of these matrix. So, and people wanted and by decomposing this A matrix into two, they could increase the performance. And they have found that these two different matrices converges to different different matrices. So these two matrices have their own roles. So this is so-called the key and Korean key stuff. And there are another component called the value matrix. It is nothing but a difference matrix, delta X. So, and in this potential model, delta X has to be trained too. So it's a bit strange model to physicists, but this is just how it is done. So, okay, so the SI to J is this conditional probability, which is a Boltzmann distribution, and they train V matrix. In that way, they train Q and K through S matrix, and they train V matrix. With these trained information gets you to from semantic dictionary curve to contextualized curve. That's the prescription, and that's how attention works. And it works successfully. So I think I have to be really brief on what we have done. So this is the attention algorithm. So what me and Sang-Han and other colleagues we have done is to insert identity matrix in this formula and decompose it. So when training stabilize, these three guys converges to some subspace of semantic manifold, and with different directions. And usually people think that this parallel direction has a meaning, and perpendicular directions are noise, so it has to be neglected or abandoned. But we decompose more closely, so this way, and we rewritten in terms of this perpendicular ordering. So we rewritten all the gradients in terms of noise, the ordering of the noise. So yeah, this is the test result, and we tested on a very small set of prediction tasks, and we got 0.56 higher success rate in prediction, in small models. So
Compared to what?
compared to the original attention model. And you may wonder if this first attention model is the best at the moment. Surprisingly, it is the best. Since it has passed almost a decade, but has been no better model than the first attention model. People have been trying to modify the model very hard. But so far, the attention model is the best. And we have, we are proposing some ways to.
You can have patent for this one.
Yes, so that's why, I applied for patent.
But you already published in the archive.
But I applied patent for a week before.
Before that house.
Yes. So it's a lot of it costs a lot of time to simulate and costs lots of money. And Sequest machine sucks, but yeah, to do it. Thank you.
Thank you for the interesting talks. So yeah, this topic was kind of new to us. So please ask any question to him, including the audience on Zoom.
What it is not fine tuning. It's not fine tuning.
Fine tuning.
Yeah. Fine tuning. Fine tuning that will fall.
Yeah, yeah, okay, so yeah, it should. We haven't optimized the parameter. Yeah, the parameter we do, we can, so we may decompose the gradient component in terms of perpendicular order, and you may decide the parallel, how much the parallel will be left, and how much the perpendicular you will neglect, and that requires a fine tuning. But we just turned it on and turned it off, that kind of thing. So it's just a crude experiment. So even with that crude experiment, we could get good validation success. So it is 0.5% prediction success doesn't look great, but as I have seen in the AI literature, they say if they succeed in 1 or 2% increase, they are really happy about it. Yeah. This is a crude experiment, so it's not that bad, I think.
So your model is better than 0.56 like that. How about speed?
Speed slows down. So yeah, it requires inverse calculations, so it costs lots of time, but it is not that bad. I mean, it increased like 2 or 3 times than the usual model, but which is acceptable if you can increase the accuracy of your output of your ChatGPT model. That means ChatGPT will give you a more precise answer. So yeah, the cost versus.
Here's another questions from June. So in your new constructions, you don't lose parallel execution? Yeah.
Can Can you tell me a little bit more about what parallel execution means? Don't lose parallel execution. Don't lose parallel execution. Parallel. Uh, I see. Okay, so I do not change the forward pass. I'm clipping gradients in the backward pass. So you can implement this method to right away. I mean, right away to the existing attention architecture without causing much change.